Tonight we're going to shatter an image that's been stuck in your head since childhood. That neat, flat picture of the solar system, with all the planets lined up on a single plane like marbles on a table. Because here's what nobody tells you. The solar system isn't flat. It never was. And the moment you start asking what's actually above it and below it, you run into a question so strange, it might keep you up tonight. Because in space, there is no up. There is no down. These directions that feel so fundamental to your existence simply don't exist out there. And yet, something is above the planets. Something is below them. And what's out there, stretching in every direction, is far larger and far stranger than most people ever imagine. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Let's start with something you've seen 1,000 times. A picture of the solar system, you know the one. The sun sits in the middle, bright and dominant, and then the planets stretch outward in a neat line. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. They're all arranged on what looks like a flat surface, like coins sitting on a table, each one orbiting the sun in a tidy circle or ellipse, all on the same level. You've seen this image in textbooks, on posters, in documentaries, on websites. It's one of the most familiar diagrams in all of science, and it's not wrong exactly, but it has done something to your brain that you probably don't realize. It has convinced you that the solar system is flat, that everything exists on a single plane, that if you could somehow fly a spaceship straight up, perpendicular to the orbits of the planets, you'd leave the solar system almost immediately because there's nothing there. You'd just be flying away from the action, away from the flat disk, where everything interesting happens. This image is so deeply embedded in how people think about space that most never question it. But tonight, we're gonna question it. We're gonna ask what that diagram is actually showing, why it looks the way it does, and what it leaves out. Because once you understand what that flat picture really represents, and what it hides, the solar system transforms from a tidy disk into something far more vast and three-dimensional than you ever imagined. So let's start at the very beginning. Why does the solar system look flat in the first place? Why do the planets orbit roughly in the same plane? This isn't a coincidence. It's not an artistic choice by the people who make diagrams. It's a real physical phenomenon, and it goes back to how the solar system formed about 4,600,000,000 years ago. Before there was a sun, before there were planets, before there was anything recognizable as our solar system, there was a cloud. A vast cloud of gas and dust floating in interstellar space. This cloud was mostly hydrogen and helium, the two lightest elements, with traces of heavier elements like carbon, oxygen, silicon, and iron mixed in. These heavier elements had been produced by earlier generations of stars that had lived and died and scattered their material across space in supernova explosions. This cloud, called a molecular cloud or sometimes a solar nebula, when we're talking specifically about the one that became our solar system, was enormous. It stretched across light years of space, and for a long time it just floated there, held in a rough equilibrium between its own gravity trying to pull it together and the internal pressure of the gas pushing outward. But something disturbed it. Maybe a nearby supernova sent a shockwave rippling through the cloud. Maybe a passing star's gravity gave it a nudge. Whatever the trigger was, part of the cloud began to collapse under its own gravity. As it collapsed, something crucial happened. The cloud began to spin. Now, it was probably already spinning very slightly. Almost everything in the universe has some tiny amount of rotation. But as the cloud contracted, that spin increased dramatically. This is the same principle that makes a figure skater spin faster when they pull their arms in. It's called the conservation of angular momentum. As the cloud got smaller, it spun faster and faster. And here's the key to understanding why the solar system is flat. As the spinning cloud collapsed, it naturally flattened out. Think about tossing pizza dough in the air and spinning it. The spin pulls the material outward along the plane of rotation, while gravity pulls it inward toward the center. The result is a flat disk. The same thing happened to the solar nebula. The cloud collapsed into a spinning disk of gas and dust, with a dense concentration of material at the center. That central concentration became the Sun. The remaining disk, spinning around the young Sun, is what astronomers call the protoplanetary disk. This disk was where everything else formed. Within the disk, particles of dust and ice began to stick together through collisions. Small grains became pebbles. Pebbles became boulders. Boulders became kilometer-sized objects called planetesimals. And planetesimals collided and merged to form protoplanets, which eventually became the planets we know today. The important thing is that all of this happened within the disk. The planets formed inside a flat rotating structure, so they inherited the disk's orientation. They all orbit in roughly the same plane because they all formed from the same flat disk of material. This plane, defined by the orbit of Earth around the Sun, is what astronomers call the ecliptic plane. It's the reference plane for the solar system. When someone says something is above or below the solar system, what they really mean is above or below this ecliptic plane. It's the baseline, the 0 point, the flat surface that the diagram is showing you. And for the 8 major planets, this reference plane works pretty well. The planets do orbit roughly in the ecliptic. They don't stray far from it. That's why the flat diagram looks convincing. It's capturing something real about the geometry of the planetary orbits. But here's where things start to get more interesting. The planets orbit roughly in the ecliptic plane, but not exactly in it. Every planet's orbit is tilted slightly relative to the ecliptic. Astronomers call this tilt the orbital inclination, and it's measured in degrees. 0 degrees means the orbit is perfectly aligned with the ecliptic. 90 degrees would mean the orbit is perpendicular to it, going straight up and over the Sun rather than around it in the usual way. Let's look at the actual numbers. Mercury, the closest planet to the Sun, has an orbital inclination of about 7 degrees. That's the highest inclination of any of the 8 major planets. 7 degrees might not sound like much, but it means Mercury's orbit takes it noticeably above and below the ecliptic plane during each trip around the Sun. At its maximum distance above or below the ecliptic, Mercury can be millions of kilometers away from the flat plane that the textbook diagram shows. Venus has an inclination of about 3.4 degrees. Earth, by definition, has an inclination of 0 degrees, because the ecliptic is defined by Earth's orbit. Mars is tilted about 1.85 degrees, Jupiter about 1.3 degrees, Saturn about 2.5 degrees, Uranus about 0.8 degrees, and Neptune about 1.8 degrees. These numbers are all small, which is why the flat diagram works reasonably well for the major planets, but they're not zero. Every planet except Earth by definition is tilted at least a little bit relative to the ecliptic. The solar system isn't perfectly flat, even when you're only looking at the 8 planets. It's more like a very thin disk, with the planets wobbling slightly above and below the central plane as they orbit. Now, 7 degrees Mercury's inclination might seem tiny, but remember the distances involved. Mercury orbits the Sun at an average distance of about 58 million kilometers. At an inclination of 7 degrees, Mercury can reach a maximum height above or below the ecliptic of about 7 million kilometers. That's almost 10 times the diameter of the Sun. So even Mercury, just one planet with a modest 7-degree tilt, can be millions of kilometers above or below the flat plane that diagrams show. The solar system diagram has already lied to you, even about the planets. But why do the planets have these small inclinations in the first place? If they all formed from the same flat disk, shouldn't they all orbit in exactly the same plane? In theory, yes. But the early solar system was chaotic. Planets didn't form in isolation and drift quietly into their final orbits. They formed in a crowded, violent environment where gravitational interactions were constant. As protoplanets grew, their gravity pulled on each other. Close encounters between forming planets could tilt their orbits slightly. Some planets may have migrated from where they originally formed, moving inward or outward through the disk, and these migrations could change their orbital inclination. Jupiter, with its enormous mass, had a particularly strong gravitational influence on everything else. As Jupiter formed and possibly migrated, it would have tugged on the other planets and scattered smaller objects, slightly tilting orbits throughout the solar system. There's also evidence that the early solar system went through a period of dramatic instability. This is sometimes called the Nice model, named after the city in France where it was developed. According to this model, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were originally in a more compact configuration, closer together and closer to the Sun. At some point, gravitational interactions between them caused their orbits to shift. Jupiter moved slightly inward. Saturn, Uranus, and Neptune moved outward. Uranus and Neptune may have even swapped positions. This reshuffling scattered enormous numbers of smaller objects throughout the solar system, and would have slightly adjusted the orbital inclinations of the planets themselves. So, the small tilts we see today are relics of a violent and chaotic youth. The solar system settled into something close to flat, but not perfectly flat. The traces of that early chaos are written in the orbital inclinations. Let's talk more about what the ecliptic plane actually is, because understanding this reference frame is crucial to understanding what above and below mean. The ecliptic plane isn't a physical object. There's no wall or surface there. It's a mathematical construct, defined by Earth's orbit around the Sun. If you traced Earth's path around the Sun, over the course of a year and then filled in the resulting ellipse to make a flat surface. That surface would be the ecliptic plane. It extends outward in all directions from the sun, like an infinitely large, perfectly flat, invisible tabletop. This is the reference plane that astronomers use when they talk about the solar system's structure. When they say an object is above the ecliptic, they mean it's on the north side of this invisible surface. When they say it's below, they mean it's on the south side. North and south here are defined by a convention. If you curl the fingers of your right hand in the direction that Earth orbits the sun, your thumb points toward ecliptic north. This points roughly toward the constellation Draco in the sky. But here's something important to understand. The ecliptic plane is a choice. It's a human choice, a convenient reference frame. There's nothing physically special about this plane compared to any other plane you might define in space. We use it because Earth is our home and Earth's orbit is a natural baseline for us. But if you lived on Mars, you might define your reference plane by Mars's orbit, which is tilted 1.85 degrees relative to ours. If you lived on Mercury, your reference plane would be tilted 7 degrees. Each planet has its own orbital plane, and none of them is more fundamentally correct than any other. This matters because when we ask what's above and below the solar system, we need to be precise about what we mean. Above and below relative to what? The ecliptic? Jupiter's orbital plane? The plane of the Milky Way galaxy? These are all different, and they give different answers. The familiar flat diagram of the solar system is showing you the ecliptic plane, but it's not showing you the only way to look at the solar system. It's showing you one perspective, chosen for convenience, not because it reveals some ultimate truth about the geometry of space. In everyday life on Earth, up and down feel absolute. Up is away from the ground, down is toward it. Gravity defines these directions for us, and they feel universal and unchangeable. But they're not. They're local. They depend on where you are. If you're standing in New York, your down points toward the center of the Earth. If you're standing in Sydney, your down also points toward the center of the Earth, but that's a completely different direction in space. Two people on opposite sides of the planet have their downs pointing in opposite directions. Down isn't absolute. It's defined by the local gravitational field. In space, away from any planet or star, there is no preferred direction. There is no up or down. You could orient yourself in any direction and it would be equally valid. The concepts of above and below only exist when you choose a reference, a plane, a surface, a direction to measure against. And in the solar system, the most common reference is the ecliptic plane. But that's a choice, not a law of physics. Now, the ecliptic plane isn't the only reference plane astronomers use. There's also the invariable plane of the solar system. This is a slightly different concept. The invariable plane is defined by the total angular momentum of the entire solar system. Angular momentum is a measure of rotational motion. Every orbiting object in the solar system contributes to the total angular momentum, and the invariable plane is the plane perpendicular to the direction of that total angular momentum. Because Jupiter contains so much of the solar system's angular momentum, being so massive and orbiting so far from the Sun, the invariable plane is very close to Jupiter's orbital plane. It's tilted about 1.6 degrees relative to the ecliptic. That's a small difference, but it's a real one. The invariable plane is in some ways a more physically meaningful reference than the ecliptic, because it takes into account the entire solar system's rotational properties, not just Earth's orbit, but both planes are nearly the same, which tells us the solar system really is quite flat, at least in its inner regions where the major planets orbit. Let me give you an analogy to help visualize what we're dealing with. Imagine a dinner plate sitting on a table. The plate is the ecliptic plane. Now place a few peas on the plate, spaced out from the center to the edge. Those are the planets. Each pea is sitting on the plate, maybe wobbling just slightly, maybe not perfectly centered on the plate's surface, but essentially on it. From the side, if you looked at the plate edge on, you'd see a thin line with tiny bumps. From above, you'd see a circular arrangement. This is what the solar system looks like when you consider just the 8 major planets. A thin disk, almost flat, with the planets arranged within it. But now, imagine that above and below the plate, there's nothing. Just empty space. That's what the textbook diagram implies. That the solar system exists on this flat plane and that's it. There's nothing interesting above or below, and that is profoundly wrong. Because the dinner plate analogy only works for the 8 major planets. Once you start looking at other objects in the solar system, objects that are smaller, more distant, or more ancient, the flat picture falls apart completely. The solar system is not a plate. It's more like a plate surrounded by a cloud. And that cloud extends in every direction, above, below, and outward, filling an enormous volume of space that the flat diagram completely ignores. But before we get to those objects, let's appreciate just how thin the planetary region really is. Because the thinness of the planetary disk is remarkable, and it tells us something important. The 8 planets orbit the Sun at distances ranging from about 58 million kilometers for Mercury to about 4,500,000,000 kilometers for Neptune. That's a span of nearly 4,400,000,000 kilometers from the innermost planet to the outermost. But the maximum height any major planet reaches above or below the ecliptic is only about 7 million kilometers, and that's Mercury, which has the highest inclination. Most planets stay much closer to the ecliptic than that. So the planetary region of the solar system is roughly 4,400,000,000 kilometers wide, but only about 14 million kilometers thick. That means the disk of planets is about 300 times wider than it is thick. That's incredibly flat. If you scaled it down to the size of a compact disk, the thickness would be closer to a sheet of paper. This extreme flatness is why the 2-dimensional diagram works so well for the planets. When something is 300 times wider than it is thick, drawing it as a flat surface doesn't lose much information. The planets really are almost perfectly aligned in a single plane. The diagram is a reasonable simplification of reality, at least for the 8 major planets. But the key phrase there is for the 8 major planets. The solar system contains far more than 8 planets. It contains dwarf planets, asteroids, comets, and billions of small icy bodies, many of which don't follow the rules of the flat disk at all. And these objects are where the story gets truly interesting, because they reveal that the solar system has a hidden dimension, a vertical dimension that the flat diagram completely erases. Even within the region of the major planets, there are hints that the solar system is more three-dimensional than it appears. The asteroid belt, which sits between Mars and Jupiter, contains millions of rocky objects. Most of these orbit roughly in the ecliptic plane, but their inclinations are generally larger than those of the planets. While the planets have inclinations of at most 7 degrees, asteroids in the main belt can have inclinations of 20 degrees or more. Some asteroids orbit on paths that take them well above and below the ecliptic, looping high over the plane of the planets before diving back down and passing through it again. Pallas, one of the largest asteroids in the main belt, has an orbital inclination of about 34.8 degrees. That's enormous compared to the planets. Pallas doesn't stay anywhere near the flat disk that the planets occupy. Its orbit takes it far above and below the ecliptic, reaching heights of hundreds of millions of kilometers above and below the plane. If you included Pallas in the standard flat diagram of the solar system, it would be way off the page, floating above or below the neat line of planets. But Pallas is almost never shown in those diagrams, precisely because it doesn't fit the flat picture. The diagrams exclude objects that break the flatness, which reinforces the illusion that the solar system is flat. This is a pattern you'll see again and again. The flat diagram of the solar system is a filtered view. It shows you the objects that happen to orbit near the ecliptic and hides the ones that don't. It's like taking a photograph of a city but only including the buildings on one street. You get a picture that suggests the city is a straight line, when in reality it extends in all directions and has far more structure than one street can show. The solar system is the same way. The ecliptic plane is one street, but there are objects above and below that street, objects that reveal the solar system's true three-dimensional nature. Another fascinating example is the dwarf planet Ceres, the largest object in the asteroid belt. Ceres has an inclination of about 10.6 degrees. Not as dramatic as Pallas, but still significantly higher than any of the major planets. Ceres moves above and below the ecliptic by tens of millions of kilometers during each orbit. Vesta, another large asteroid, has an inclination of about 7.1 degrees, similar to Mercury. These are substantial tilts that would be clearly visible if you could watch these objects from outside the solar system. The point here is that the flat diagram is a gross simplification even within the inner solar system. It works well enough for the 8 major planets, but it fails for asteroids, and it will fail even more spectacularly as we move outward to the more distant and exotic regions of the solar system. Let's talk about another subtlety that the flat diagram hides. The planets don't just orbit in slightly different planes. Their orbital planes also precess. Precession is a slow wobble, like a spinning top that gradually changes the direction its axis points. Each planet's orbital plane slowly rotates over time, driven by the gravitational pull of the other planets, especially Jupiter and Saturn. This means the ecliptic plane itself isn't fixed. It shifts over thousands of years. The amount of shift is small, but it's real. Over tens of thousands of years, the orientation of the planetary orbit slowly changes, and with it, the definition of above and below changes too. This precession is another reminder that the flat diagram is a snapshot, not a permanent truth. The solar system's geometry is dynamic. The planes of the orbits are not locked in place. They shift, they wobble, they evolve. The flatness you see today is a momentary arrangement, a frozen instant in a slow gravitational dance that's been going on for billions of years and will continue for billions more. Even the sun itself contributes to the three-dimensional complexity. The sun isn't a stationary point at the center of a flat disk. It has its own motion. The sun orbits the center of the Milky Way galaxy at a speed of about 230 kilometers per second. As it moves, it carries the entire solar system with it. But the sun doesn't move in a perfectly flat orbit around the galaxy. It bobs up and down through the galactic plane, oscillating above and below the midplane of the Milky Way over a period of about 60 to 70 million years. This means the entire solar system, ecliptic plane and all, is itself moving up and down relative to a larger reference plane, the plane of the galaxy. We'll explore this in much more detail later, but for now, the takeaway is that even the frame of reference we use to define above and below, the ecliptic plane, is itself tilted and moving within a larger cosmic structure. So where does all this leave us? We started with the familiar flat diagram of the solar system, and we've begun to peel back the layers of simplification. The diagram is useful. It captures something real about the geometry of the planetary orbits. The 8 major planets really do orbit roughly in the same plane, a consequence of their formation from a flat protoplanetary disk. But even among the major planets, there are small but real inclinations that take them above and below the ecliptic. In the asteroid belt, those inclinations become much larger, and the ecliptic plane itself is not fixed or absolute. It's a human-defined reference frame that shifts over time and is tilted relative to larger structures in the galaxy. The flat diagram is a starting point, not an ending point. It shows you the solar system's skeleton, the basic framework of planetary orbits that defines its large-scale geometry. But the full solar system is far richer, far more complex, and far more three-dimensional than that skeleton suggests. The objects that break the flatness, the asteroids with steep inclinations, the comets that come screaming in from bizarre angles, the distant icy bodies that orbit in planes nothing like the ecliptic. These are the objects that reveal what actually lies above and below the neat picture you've always been shown. And as we move outward from the planets, past the asteroid belt, past the orbits of the giant planets, into the cold and distant reaches of the outer solar system, the flat picture doesn't just become incomplete, it becomes almost meaningless. Because out there, in the dark, spaces beyond Neptune, the solar system opens up into something the textbook diagram never prepared you for. Something vast, something spherical, something that extends above and below the planetary plane by distances so enormous they stretch nearly halfway to the nearest star. The flat disk of planets that you thought was the solar system is only the thinnest, innermost layer of a structure far larger and far more three-dimensional than anything the standard diagram could ever show you. Now let's leave the familiar territory of the 8 planets and travel outward, past Neptune, into the cold, dark frontier of the outer solar system. Because this is where the flat picture you've carried in your head your entire life doesn't just bend. It shatters. Everything we talked about so far, the small orbital tilts of the planets, the modest inclinations of certain asteroids, those were gentle hints that the solar system has a vertical dimension. What comes next is not a hint. It's a declaration. The outer solar system is a place where objects orbit at steep, dramatic angles, where the ecliptic plane becomes almost irrelevant, and where the true three-dimensional architecture of our solar system finally reveals itself. The first sign that something strange is happening comes from an old friend, Pluto. For 76 years, from its discovery in 1930 until its reclassification in 2006, Pluto was considered the 9th planet. School children memorized it. Posters included it. It was the last stop on the flat diagram, sitting at the edge of the planetary line, a small frozen world at the end of the row. But Pluto was never comfortable in that lineup. It never really fit. And one of the biggest reasons it didn't fit is its orbit. Pluto's orbital inclination is about 17 degrees relative to the ecliptic. That's more than twice Mercury's inclination, which is the highest among the 8 major planets. 17 degrees is a dramatic tilt. It means that Pluto's orbit takes it far above and below the plane where the other planets travel. At its greatest distance from the ecliptic, Pluto can be more than 1,200,000,000 kilometers above or below the flat disk of the planets. To put that in perspective, that's more than 8 times the distance from Earth to the Sun. Pluto doesn't just wobble slightly above and below the ecliptic. It soars far beyond it, looping high above the planetary plane on one side of its orbit, and then diving deep below it on the other side. If you could watch Pluto's orbit from the side, looking at the solar system edge on, you would see the 8 planets tracing nearly flat paths, barely deviating from the central plane. And then you'd see Pluto's path slicing through that plane at a steep angle, like a hula hoop leaning against a table. Pluto crosses the ecliptic twice during each of its 248 Earth-year orbits, spending half its time above the plane and half below it. The standard flat diagram can't show this. It has no room for an object that spends most of its time far from the ecliptic. So the diagram either excludes Pluto entirely or places it on the flat line with everything else, hiding its true orbital geometry. But Pluto's orbit is strange in another way too. It's highly eccentric, meaning it's stretched into an elongated ellipse rather than being close to a circle. At its closest approach to the Sun, called perihelion, Pluto comes within about 4,400,000,000 kilometers. That's actually inside Neptune's orbit. At its farthest point, aphelion, it's about 7,400,000,000 kilometers from the Sun. This huge variation in distance, combined with the steep inclination, means Pluto's path through space is nothing like the neat circular orbit shown in textbook diagrams. It's a tilted, stretched loop that occupies a very different region of space from the other planets, and Pluto was just the beginning. Because Pluto, it turns out, is not alone out there. It's one member of a vast population of icy objects beyond Neptune, and many of them have orbits that are even more inclined, even more eccentric, and even more dramatic than Pluto's. This is the Kuiper Belt, and its discovery fundamentally changed our understanding of the solar system's shape. The Kuiper Belt is a region of space extending from roughly the orbit of Neptune, about 30 astronomical units from the Sun, to about 50 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, About 150 million kilometers. It's a vast ring of icy bodies, remnants from the formation of the solar system that never coalesced into a planet. The existence of the Kuiper Belt was predicted long before it was confirmed. In 1951, astronomer Gerard Kuiper suggested that a belt of small icy bodies might exist beyond Neptune. But it wasn't until 1992 that astronomers David Jewitt and Jane Liu discovered the first Kuiper Belt object other than Pluto, a small body designated 1992 QB1. Since then, more than 2,000 Kuiper Belt objects have been discovered, and astronomers estimate that the belt contains hundreds of thousands of objects larger than 100 kilometers in diameter, and possibly trillions of smaller ones. Now here's what matters for our story. The Kuiper Belt is not flat. It's much thicker and more three-dimensional than the planetary region of the solar system. While the 8 planets orbit within a disk that's only a few degrees thick, the Kuiper Belt contains objects with a wide range of inclinations. Some orbit close to the ecliptic, but many don't. The overall structure of the Kuiper Belt is more like a thick donut than a thin disk. Objects within it can have inclinations of 5, 10, 20, or even 30 degrees or more. Astronomers divide Kuiper Belt objects into several categories based on their orbital characteristics, and each category tells us something different about the solar system's three-dimensional structure. The classical Kuiper Belt objects, sometimes called cubawanos after the first one discovered, orbit between about 42 and 48 astronomical units from the Sun in relatively circular orbits. These objects have a range of inclinations that divides them into 2 populations. The cold classical population has low inclinations, typically less than 5 degrees. These objects orbit close to the ecliptic, almost like a thin extension of the planetary disk. But the hot classical population has much higher inclinations, up to 30 degrees or more. These objects were likely scattered into their current orbits by gravitational interactions with Neptune during the early solar system. The fact that there are 2 distinct populations within the same region of space, one flat and one puffy, tells us that the Kuiper Belt has a complex vertical structure. It's not a single flat ring, it's a layered structure with a thin component embedded within a thicker one. Then there are the resonant Kuiper Belt objects. These are bodies whose orbital periods are in a simple ratio with Neptune's orbital period. Pluto is the most famous example. Its orbital period is in a 3:2 ratio with Neptune's, meaning Neptune goes around the Sun 3 times for every 2 times Pluto does. This 3:2 resonance keeps Pluto and Neptune from ever colliding, even though their orbits cross. Other resonant populations exist at different ratios. Objects in these resonances can have a wide range of inclinations, from nearly flat orbits to steeply tilted ones. The resonances can actually protect objects at high inclinations from being ejected from the solar system, allowing them to survive on tilted orbits for billions of years that would otherwise be unstable. But the most dramatic departure from the flat picture comes from a population called the scattered disk. These are objects that have been flung onto highly eccentric and highly inclined orbits by gravitational encounters with Neptune. Scattered disk objects can have orbital distances ranging from about 30 astronomical units at their closest to hundreds or even thousands of astronomical units at their farthest. Their inclinations can be extreme. Some scattered disk objects orbit at inclinations of 40 degrees or more. Eris is the most famous scattered disk object. Discovered in 2005 by astronomer Mike Brown and his team, Eris was the discovery that ultimately led to Pluto's reclassification as a dwarf planet. Eris is actually slightly more massive than Pluto, though slightly smaller in diameter. Its orbital inclination is about 44 degrees. 44 degrees. That's nearly halfway to being perpendicular to the ecliptic. Eris's orbit takes it so far above and below the planetary plane that trying to include it in the standard flat solar system diagram would be absurd. At its maximum distance from the ecliptic, Eris can be billions of kilometers above or below the plane where the planets orbit. It spends most of its 559-year orbit far from the ecliptic, soaring above or diving below the flat disk that the textbook diagram shows. Eris's orbit is also highly eccentric. At perihelion, it comes within about 38 astronomical units of the Sun, just inside the outer edge of the Kuiper Belt. At aphelion, it's about 98 astronomical units away, more than twice Pluto's average distance from the Sun. This enormous orbit, steeply tilted and wildly stretched, occupies a volume of space that the flat diagram simply cannot represent. Eris is part of the solar system. It orbits the Sun. It's made of the same primordial material as the planets, but it lives in a completely different geometric reality from the one the flat picture shows. And Eris isn't even the most extreme example. There are scattered disk objects with inclinations exceeding 50 or 60 degrees. Some have orbits that take them so far from the ecliptic that they spend centuries at a time far above or below the planetary plane, invisible to surveys that concentrate their observations near the ecliptic. We've almost certainly only found a fraction of the scattered disk population. The objects we've found are the ones that happen to be near the ecliptic when we looked. The ones far above or below the ecliptic at great distances from the Sun are extremely faint and extremely hard to find. The scattered disk could contain far more mass and far more objects than we currently know about. There's another population that pushes the three-dimensional nature of the solar system even further. These are called detached objects, or sometimes extended scattered disk objects. These bodies have orbits so distant that they're no longer significantly influenced by Neptune's gravity. Their perihelia, their closest approaches to the Sun, are far enough out that Neptune can't perturb them. Something else must have shaped their orbits. Maybe it was a passing star in the distant past. Maybe it was the combined gravity of many small perturbations over billions of years. Maybe it was the influence of a large, undiscovered planet in the outer solar system, which some astronomers have hypothesized and dubbed Planet 9. Sedna is the most famous detached object. Discovered in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz, Sedna has one of the most extreme orbits of any known solar system object. Its perihelion is about 76 astronomical units from the Sun, far beyond Neptune's influence. Its aphelion is a staggering 937 astronomical units. That's roughly 140 billion kilometers from the Sun. Sedna takes about 11,400 Earth years to complete one orbit. Its inclination is about 11.9 degrees, which is relatively modest compared to Eris, but its enormous distance means that it occupies a vast volume of space far from the ecliptic. Another remarkable detached object is 2012 VP113, which has a perihelion of about 80 astronomical units and a semi-major axis of about 265 astronomical units. Its inclination is about 24 degrees. These detached objects hint at a population of bodies orbiting in the deep outer solar system well beyond the Kuiper Belt, in orbits that can be significantly tilted relative to the ecliptic. They're the furthest confirmed members of the solar system before we reach the hypothesized Oort Cloud, and they suggest that the transition from the relatively flat inner solar system to the spherical outer solar system is gradual, with inclinations getting larger and larger as you move outward. Now let's talk about comets, because comets provide some of the most dramatic evidence that the solar system extends far above and below the ecliptic plane. There are two main types of comets, and they tell very different stories about the solar system's geometry. Short period comets, those with orbital periods of less than 200 years, mostly come from the Kuiper Belt and scattered disk. They tend to have relatively low inclinations, orbiting within about 30 degrees of the ecliptic. This makes sense because they were scattered inward from the Kuiper Belt region, which, while thicker than the planetary disk, is still somewhat concentrated near the ecliptic. But there are exceptions. Halley's Comet, which has an orbital period of about 75 to 79 years, and an inclination of about 162 degrees, is technically short period by its timing, but its retrograde orbit suggests it originally came from the Oort Cloud rather than the Kuiper Belt. An inclination greater than 90 degrees means the object orbits in the opposite direction from the planets. It's called a retrograde orbit. Halley's Comet orbits the Sun backward relative to the planets, and its orbit is tilted significantly from the ecliptic. Every time Halley's Comet visits the inner solar system, it's a vivid reminder that the solar system contains objects moving on paths nothing like the neat prograde orbits of the planets. Long-period comets are even more revealing. These are comets with orbital periods greater than 200 years, sometimes stretching to millions of years. They come from much farther away, from the outermost reaches of the solar system. And here's the crucial point. Long-period comets come from every direction. Their orbital inclinations span the full range from 0 to 180 degrees. They come in from above the ecliptic, from below it, from every angle imaginable. Some orbit in the same direction as the planets. Others orbit backward. Their paths are essentially random in orientation. This is incredibly important for understanding what lies above and below the solar system. If long-period comets come from all directions equally, then their source, the reservoir from which they originate, must be spherical. It must surround the solar system in every direction, above, below, and all around, with roughly equal density in all directions. A flat disk source would produce comets that mostly come from near the ecliptic. Only a spherical source can produce comets arriving from every direction. This was one of the first and strongest pieces of evidence for the existence of the Oort Cloud, the vast spherical shell of icy bodies that surrounds the entire solar system. But we'll talk about the Oort Cloud in detail shortly. For now, the point is that comets demonstrate that the solar system is not a flat structure. Objects orbit the sun at every possible angle. The flat diagram shows you only the most orderly objects, the planets, which happen to orbit near the ecliptic. It hides the chaotic, tilted, three-dimensional reality of the outer solar system. Let me give you a way to visualize all of this. Imagine you're floating in space, far above the ecliptic plane, looking down at the solar system from the north. From this vantage point, you see the sun at the center, and the 8 planets orbiting in nearly circular paths, all going in the same direction. It looks like the flat diagram, a set of concentric rings around a central point. Now zoom out further, you start to see the Kuiper Belt, a broader, thicker ring beyond Neptune's orbit. Some objects in this ring are in the plane, but others are above and below your line of sight. Their orbits tilted so they trace paths that loop above and below the planetary plane. The neat flat picture is getting fuzzy around the edges. Now change your vantage point. Instead of looking from above, look at the solar system edge on. From this perspective, the planets form a thin line, a narrow band centered on the ecliptic. But the Kuiper Belt objects spread out above and below this line, forming a thicker band, and the scattered disk objects spread out even further, some orbiting at angles so steep they're nearly perpendicular to the planetary line. The neat thin line of planets is surrounded by a diffuse cloud of objects that extends far above and below it. The solar system, seen edge on, is not a thin disk. It's a thin disk embedded within a much thicker, much more extended distribution of objects. And it gets even more dramatic. Among the more distant objects, there are a few that challenge our understanding of solar system formation entirely. In 2008, astronomers discovered an object designated 2008 KV42, nicknamed DRAC. It orbits the sun in a retrograde direction, with an inclination of about 104 degrees. This means it's not only orbiting at a steep angle to the ecliptic, but going around the sun in the opposite direction from the planets. It was one of the first trans-Neptunian objects found to have a retrograde orbit. Its existence suggests that some outer solar system objects have been scattered so violently that their orbits have been completely flipped. They've been turned upside down relative to the planetary plane. How does this happen? Gravitational encounters with the giant planets, especially Neptune, can gradually increase an object's inclination over millions of years. But to flip an orbit completely into retrograde requires extreme perturbation. Some models suggest that interactions with passing stars, or the gravitational influence of the galactic tide, the combined gravity of all the matter in the Milky Way, can flip orbits over very long time scales. These retrograde trans-Neptunian objects may be transitional objects, bodies that started in the scattered disk or Oort Cloud and have been gravitationally twisted into their current bizarre orbits. Their existence proves that the solar system contains objects orbiting at literally every possible angle, from perfectly flat to completely inverted. Let's also consider the dwarf planets, because each one tells us something about the solar system's vertical extent. Make, discovered in 2005, orbits in the Kuiper Belt with an inclination of about 29 degrees. Haumea, also discovered in 2005, has an inclination of about 28 degrees. Gong Gong, a large trans-Neptunian object, has an inclination of about 30.7 degrees. These are all substantial tilts, far more than any of the 8 major planets, and these are just the largest objects. The smaller Kuiper Belt objects span an even wider range of inclinations. There's an important pattern here. As you move outward from the Sun, away from the orderly realm of the major planets, the range of orbital inclinations increases. The inner solar system is flat. The asteroid belt is somewhat thicker. The Kuiper Belt is thicker still. The scatter disk is even more extended vertically. And beyond that, as we'll see, the solar system becomes fully spherical. The solar system doesn't have a sharp boundary between flat and round. Instead, it gradually puffs up as you move outward, like a disk that slowly inflates into a sphere. This gradient from flat to spherical reflects the history of gravitational interactions in the solar system. Close to the Sun, where the planets orbit, gravitational forces are strong and ordered. The planets formed from a flat disk, and their gravity keeps most nearby objects relatively close to the ecliptic. But farther out, where the Sun's gravity is weaker and the giant planet's influence is less dominant, objects can be scattered into higher inclination orbits by random gravitational encounters. The farther out you go, the easier it is for objects to end up on tilted orbits, because there's less gravitational authority imposing order. The outer solar system is a frontier where the flat organization of the inner system gradually gives way to three-dimensional chaos. This also explains why the flat diagram is so misleading. The diagram was designed to show the planets, and for the planets, it works. But the planets are only the innermost, most orderly layer of the solar system. They're the part where flatness prevails. If the diagram tried to show the full solar system, including the Kuiper Belt, scattered disk, and detached objects, it would need a third dimension. It would need depth. And the flat picture on a page can't provide that. So the diagram just ignores everything that doesn't fit its flat framework, giving you a profoundly incomplete view of the solar system you actually live in. There's one more thing worth mentioning before we move further outward. The hypothetical Planet 9. In 2016, astronomers Konstantin Batygin and Mike Brown published a paper suggesting that the unusual orbits of several distant trans-Neptunian objects could be explained by the gravitational influence of a large undiscovered planet far beyond Neptune. If Planet 9 exists, it would have a mass of about 5 to 10 times Earth mass and orbit at a distance of about 400 to 800 astronomical units from the Sun. Its orbital inclination is predicted to be about 15 to 25 degrees relative to the ecliptic. Planet 9 has not been found. Despite extensive searches, no one has directly observed it. It remains hypothetical, but the gravitational evidence is intriguing. The clustering of certain distant orbits is difficult to explain without some large perturbing body. If Planet 9 does exist, it would be yet another object that breaks the flat picture. A massive planet orbiting the Sun at a steep angle far above and below the ecliptic plane. Invisible to most surveys because it's so far away and so far from where we typically look. Whether Planet 9 exists or not, the objects we've already found are enough to completely rewrite our mental image of the solar system. The flat diagram shows you 8 planets in a thin disk. Reality gives you 8 planets in a thin disk surrounded by a thick belt of icy objects with inclinations up to 30 degrees, surrounded by a scattered population with inclinations up to 45 degrees or more, surrounded by detached objects on enormous orbits that extend thousands of astronomical units from the Sun, all threaded through by comets arriving from every possible direction. The solar system is not a flat picture, it's a 3-dimensional structure, thin in the middle and increasingly extended in the vertical direction as you move outward. And we haven't even gotten to the most dramatic part yet. Because everything I've described so far, the Kuiper Belt, the scattered disk, the detached objects, all of these still have some memory of the original flat disk from which the solar system formed. Their inclinations are higher than the planets, but most still prefer to be somewhat near the ecliptic. There's still a concentration of objects around the flat plane, even if the distribution is much thicker. But beyond all of these, in the outermost reaches of the solar system, even that last trace of flatness disappears. Out there, the solar system becomes something the flat diagram could never show you. It becomes a sphere, and that sphere, stretching in every direction, above, below, and outward, is so vast that it makes everything we've discussed so far look tiny by comparison. Now we go beyond everything you've ever seen in a solar system diagram, beyond the planets, beyond the Kuiper Belt, beyond the scattered disk, beyond even the most distant detached objects like Sedna. We go out to a place so remote, so cold, so dark, that no telescope has ever directly seen a single object there. And yet, we know it exists, we know it's enormous, and we know it changes everything about what lies above and below the solar system. This is the Oort Cloud, and it is where the flat picture of the solar system dies completely, replaced by something so vast and so fundamentally different in shape that it challenges everything you thought you knew about our cosmic neighborhood. Let's set the stage with distance, because without understanding how far away the Oort Cloud is, nothing else about it will make sense. The innermost planet, Mercury, orbits at about 0.4 astronomical units from the Sun. Neptune, the outermost major planet, orbits at about 30 astronomical units. The Kuiper Belt extends to roughly 50 astronomical units. Sedna, one of the most distant known objects, reaches about 937 astronomical units at the far end of its orbit. These are already enormous distances. 1 astronomical unit, the distance from Earth to the Sun, is about 150 million kilometers. Sedna at aphelion is roughly 140 billion kilometers from the Sun. That's far beyond anything shown in the standard solar system diagram. But the Oort Cloud begins at roughly 2,000 to 5,000 astronomical units from the Sun and extends outward to somewhere between 50,000 and 100,000 astronomical units. Let me translate that into more familiar terms. 100,000 astronomical units is approximately 1.6 light years. The nearest star to the Sun, Proxima Centauri, is about 4.24 light years away. So the outer edge of the Oort Cloud reaches nearly 40% of the way to the nearest star. It stretches so far from the Sun that it exists in a kind of no man's land between our solar system and the next star system. To grasp this scale, think about it proportionally. If the orbit of Neptune were the size of a quarter, roughly 2.5 centimeters across, the outer edge of the Oort Cloud would be about 80 meters away. You'd need to walk the length of a football field to reach the boundary of the solar system as defined by the Oort Cloud. And between that quarter and that distant boundary, there would be almost nothing visible, just emptiness, with scattered invisible specks of ice drifting in the darkness. The Kuiper Belt, the scattered disk, all the objects we discussed earlier, they would fit within a few centimeters of that quarter. The Oort Cloud dominates the solar system by volume. It is the solar system, at least in terms of the space it occupies. Everything else, the planets, the asteroid belt, the Kuiper Belt, all of it is just a tiny kernel at the center of this enormous structure. The Oort Cloud was first proposed in 1950 by Dutch astronomer Jan Oort. He noticed something peculiar about long-period comets. Comets with orbital periods of more than 200 years. When he calculated their orbits backward to determine where they came from, he found that many of them originated from roughly the same enormous distance, somewhere between 20,000 and 100,000 astronomical units from the Sun. Furthermore, these comets came from every direction in the sky. They weren't concentrated near the ecliptic like the planets and most Kuiper Belt objects. They arrived from above, from below, from every angle. Some came in prograde, orbiting the Sun in the same direction as the planets. Others came in retrograde, orbiting backward. Their orbital planes were essentially random. This pattern, comets arriving from a consistent distance but from all directions, led Oort to propose that the solar system is surrounded by a vast spherical cloud of icy bodies. Not a disk, not a ring, not a belt, but a sphere. A shell of trillions of small frozen objects enclosing the entire solar system, like a cosmic bubble. This is the Oort Cloud, and its spherical shape is the single most important thing to understand about what lies above and below the solar system. Think about what this means. When you look at the flat diagram of the solar system and ask what's above it and below it, the answer, at large enough distances, is the Oort Cloud. There is just as much solar system material directly above the Sun's north pole as there is in the plane of the planets. There is just as much material directly below the Sun's south pole as there is along the ecliptic. The solar system, at its largest scale, has no preferred plane. It's not flat, it's round. This is a radical departure from the flat picture. The ecliptic plane, which defines above and below for the inner solar system, becomes almost meaningless at Oort Cloud distances. There's no reason to prefer one direction over another. The cloud is roughly the same in all directions. If you traveled straight up from the ecliptic, perpendicular to the planetary orbits, you wouldn't leave the solar system. You'd travel through the Oort Cloud for more than a light year before reaching its outer edge. If you traveled along the ecliptic plane outward past Neptune, you'd also travel through the Oort Cloud for more than a light year. The distance is roughly the same in every direction because the structure is spherical. Let me be more specific about the Oort Cloud structure because astronomers believe it actually has two components. The outer Oort Cloud, sometimes called the isotropic Oort Cloud, is the spherical shell that Jan Oort originally proposed. It extends from roughly 20,000 to 100,000 astronomical units. The objects in this region have orbits that are essentially randomly oriented. Their inclinations span the full range from 0 to 180 degrees. There's no concentration near the ecliptic, no preferred plane at all. This outer shell is the source of most long-period comets. The inner Oort Cloud, sometimes called the Hills Cloud after astronomer Jack Hills, who proposed it in 1981, is thought to be a denser, more disk-like or slightly flattened structure between roughly 2,000 and 20,000 astronomical units. The inner Oort Cloud may have some residual flattening, a slight preference for the ecliptic plane left over from the original protoplanetary disk. But even this inner component is much thicker and more three-dimensional than the Kuiper Belt. It's a transition zone between the somewhat flattened scattered disk and the perfectly spherical outer Oort Cloud. The objects in the Oort Cloud are believed to be icy bodies, similar in composition to comets and Kuiper Belt objects. They're made of water ice, frozen methane, frozen ammonia, and frozen carbon dioxide mixed with rocky and dustite material. Most are probably small, just a few kilometers across, similar in size to comets, but there might also be larger objects out there, perhaps even dwarf planet-sized bodies that we've never detected because they're so far away and so faint. How many objects are in the Oort Cloud? Estimates vary widely because we've never directly observed a single Oort Cloud object in situ. Everything we know about it comes from the comets it occasionally sends toward the inner solar system. Based on the rate at which long-period comets appear, astronomers estimate the outer Oort Cloud contains somewhere between several hundred billion and 2 trillion objects larger than about 1 kilometer. The inner Oort Cloud might contain 5 to 10 times more than that. Some estimates put the total number of objects in the entire Oort Cloud at several trillion. The total mass is harder to estimate, but it's probably somewhere between 1 and 40 times the mass of Earth. That might not sound like much compared to Jupiter, which has 318 times Earth's mass. But that mass is spread across a volume of space that is almost incomprehensibly large. Let's think about that volume. The outer Oort Cloud is a spherical shell with an inner radius of about 20,000 astronomical units and an outer radius of about 100,000 astronomical units. The volume of this shell is roughly 4.2 times 10 to the 42nd cubic kilometers. That's a number so large that it has no intuitive meaning. Even the total volume of the orbits of all 8 planets is tiny compared to this. The Oort Cloud occupies a volume of space that dwarfs the rest of the solar system by a factor of millions or more. Despite this enormous volume, the Oort Cloud is incredibly sparse. Trillions of objects sounds like a lot, and it is. But spread across such a vast volume, the average distance between Oort Cloud objects is probably tens of millions of kilometers. If you were somehow transported into the Oort Cloud and looked around, you would see nothing. Absolutely nothing. No nearby objects, no distant glow, nothing but darkness in every direction. The sun would appear as a bright star, but not overwhelmingly bright. At 50,000 astronomical units, the sun would be much fainter than it appears from Earth, appearing as just another star amongst the thousands visible in the night sky. You would feel profoundly, terrifyingly alone. The nearest Oort Cloud object might be farther away than the Earth is from the sun, and it will be far too small and dark to see with the naked eye. This emptiness is why the Oort Cloud has never been directly observed. The objects are too small, too faint, and too far away for any current telescope to detect. We infer its existence entirely from the comets that fall inward from it. When something disturbs an Oort Cloud object, nudging it out of its distant orbit and sending it falling toward the Sun, it becomes a long-period comet. As it approaches the inner solar system and the Sun's heat begins to vaporize its ices, it develops a coma and a tail and becomes visible. But it started its journey in the Oort Cloud, in total darkness, trillions of kilometers from the Sun, in a region of space that the flat diagram has never shown you. What causes Oort Cloud objects to fall inward and become comets? Several things. The gravity of passing stars is one of the most important. Stars in the Sun's neighborhood are constantly moving, and occasionally one passes close enough that its gravity perturbs objects in the outer Oort Cloud. These perturbations are gentle, just slight nudges. But at Oort Cloud distances, the objects are so loosely bound to the Sun that even a gentle nudge can change their orbit significantly. A small change in velocity can send an Oort Cloud object on a new trajectory that carries it into the inner solar system over the course of millions of years. The galactic tide is another important influence. This is the differential gravitational pull of the Milky Way galaxy itself. The galaxy isn't pulling on the solar system uniformly. The side closer to the galactic center feels a slightly stronger pull than the side farther away. This difference in gravitational force, the tidal effect, slowly torques the orbits of distant Oort Cloud objects, changing their shapes and orientations over millions of years. The galactic tide is actually the dominant perturber for the outer Oort Cloud, more important than passing stars for most objects. It systematically rotates orbits, and over long time periods, it can funnel objects into orbits that bring them close to the Sun. Giant molecular clouds, massive concentrations of gas and dust in the galaxy, can also perturb the Oort Cloud when the solar system passes through or near them. These encounters are rarer than stellar passages, but can be more disruptive because molecular clouds are so massive. A close encounter with a giant molecular cloud could potentially send a shower of comets into the inner solar system, dramatically increasing the impact rate on Earth and the other planets. Some scientists have speculated that periodic comet showers caused by such encounters might be linked to mass extinction events in Earth's biological history, though this connection remains controversial and unproven. Now, let's ask the question that brought us here. What actually lies above and below the solar system? At the distance of the Oort Cloud, the answer is stunning in its simplicity. Above the solar system is more solar system. Below the solar system is more solar system. The Oort Cloud extends in every direction, including directly above and below the ecliptic plane, to distances of more than a light year. If you could travel straight up from the Sun, perpendicular to the plane of the planets, you would pass through scattered Oort Cloud objects for roughly 100,000 astronomical units, about 1.6 light years, before reaching the outer boundary, where the Sun's gravitational influence fades and interstellar space truly begins. This means that the solar system, defined as the region of space gravitationally dominated by the Sun, is not a flat disk a few billion kilometers across. It's a sphere nearly 2 light years in radius. The flat part, the planetary disk, occupies only the innermost sliver of this sphere. The rest of the solar system's volume, the overwhelming majority of it, is the Oort Cloud, and it extends above and below the ecliptic just as far as it extends along it. Now, let's talk about what lies beyond the Oort Cloud, because eventually even the Sun's gravitational reach has a limit. Beyond the outermost Oort Cloud objects, the Sun's gravity becomes weaker than the gravitational influences of other stars and the galaxy itself. Objects beyond this boundary are no longer bound to the Sun. They drift freely through interstellar space. But the transition from solar system to interstellar space isn't sharp. There's no wall or fence marking where one ends and the other begins. The density of Oort Cloud objects slowly decreases as you move outward, and the Sun's gravitational influence fades gradually until other gravitational sources dominate. There is, however, a different kind of boundary that's worth discussing: the heliopause. This is the boundary where the solar wind, the constant stream of charged particles flowing outward from the Sun, meets the interstellar medium, the thin gas that fills the space between stars. The heliopause is much closer than the Oort Cloud, at about 120 to 140 astronomical units from the Sun. Voyager 1 crossed the heliopause in 2012, and Voyager 2 crossed it in 2018, making them the first human-made objects to enter interstellar space by this definition. But the heliopause is not the edge of the solar system. It's the edge of the Sun's wind, the boundary of the bubble of charged particles that the Sun blows into space. The Oort Cloud extends far, far beyond the heliopause. Voyager 1, despite having crossed into interstellar space, as defined by the solar wind boundary, is still deep within the solar system, as defined by the Sun's gravitational influence. It would need to travel for roughly another 20,000 years at its current speed to reach the inner edge of the Oort Cloud, and tens of thousands of years more to pass through it completely. This highlights an important distinction. The solar system has multiple boundaries depending on how you define it. If you define it by the solar wind, it ends at the heliopause, about 120 astronomical units out. If you define it by the major planets, it ends at Neptune, about 30 astronomical units out. If you define it by the Sun's gravitational dominance, it ends at the outer edge of the Oort Cloud, about 100,000 astronomical units out. The flat diagram typically shows only the first 30 to 50 astronomical units, the planetary region, and maybe a hint of the Kuiper Belt. The true gravitational solar system is more than 2,000 times larger than what the diagram shows. What does the space above and below the solar system actually look like at these enormous distances? If you could somehow travel to a point 100,000 astronomical units directly above the Sun, perpendicular to the ecliptic, you'd be at the outer edge of the Oort Cloud. Looking down, you might be able to see the Sun as a moderately bright star. The planets would be completely invisible, far too close to the Sun, and far too small and faint to detect. The entire Kuiper Belt, with all its thousands of known objects, would be an invisible speck. You would see nothing of the solar system except the Sun itself, and even that would appear as just another star. Looking around you, you'd see stars in every direction. The constellations would look slightly different because you'd have shifted your position by 1.6 light years relative to Earth. but the overall appearance of the sky would be similar. You might not even be able to identify which star was the sun without careful measurement. There would be no sign that you were still within the solar system. The only evidence would be the occasional Oort Cloud object drifting silently through the void, invisible to your eyes, detectable only with sensitive instruments. Looking outward, away from the sun, you'd see the interstellar medium. This is the thin gas and dust that fills the space between stars. It's incredibly sparse, averaging only about 1 atom per cubic centimeter in our region of the galaxy. That's a far better vacuum than anything we can create on Earth. The interstellar medium isn't uniform. It has denser regions and less dense regions. The Sun is currently traveling through a relatively low-density region called the local bubble, a cavity in the interstellar medium thought to have been carved out by supernova explosions millions of years ago. The local bubble is about 300 light-years across and contains gas that's thinner and hotter than the average interstellar medium. Above and below the ecliptic plane, at distances beyond the Oort Cloud, the environment is essentially the same interstellar medium that surrounds the solar system in every direction. There's nothing special about the space above or below the solar system compared to the space alongside it. It's all interstellar space, filled with the same thin gas, the same dust, the same cosmic rays, the same faint background of starlight. The only difference is that along the ecliptic plane, you might encounter the extremely sparse outer Kuiper Belt and scattered disk objects before reaching the Oort Cloud, while straight above or below, you'd enter the Oort Cloud more directly because there's no flattened disk population in the way. This uniformity is actually profound. It tells us that the solar system at its largest scale doesn't have a preferred orientation relative to interstellar space. The ecliptic plane, which feels so fundamental from our perspective on Earth, has no special significance to the interstellar medium. The gas between stars doesn't know or care where Earth's orbital plane is. The Oort Cloud surrounds us in every direction with roughly equal density. Above, below, left, right. These distinctions are meaningless at Oort Cloud distances and beyond. But there is one more environment worth describing, because it's often overlooked. Between the heliopause at about 120 astronomical units and the inner edge of the Oort Cloud at about 2,000 astronomical units, there's a vast region of space that belongs to the solar system gravitationally, but lies beyond the reach of the solar wind. This region is sometimes called the heliosheath's outer boundary environment, though it doesn't have a catchy name. It's a kind of transitional zone. Inside the heliopause, the sun's charged particles dominate the local environment. Outside it, the interstellar medium's particles dominate, but the sun's gravity still holds sway. In this transition zone, above and below the ecliptic, you'd find almost nothing. The occasional scattered disk object or detached object might be out there on a highly inclined orbit, but the density of objects is extremely low. This is one of the emptiest regions of the solar system. It's too far out for the Kuiper Belt, and too close for the main Oort Cloud. It's a void within our own system, a vast empty shell separating the known outer solar system from the hypothesized Oort Cloud. And yet, even this emptiness tells us something. It tells us that the solar system is not a continuous distribution of material from the sun outward. It has structure. It has gaps. The inner solar system is dense with planets and asteroids. The Kuiper Belt is moderately populated with icy bodies. Then there's a long gap with very few known objects. Then, presumably, the Oort Cloud begins, with its trillions of icy bodies spread across an enormous spherical volume. The solar system's matter is arranged in layers, each layer thicker and more three-dimensional than the last, with vast empty spaces between them. This layered structure is important for understanding what lies above and below us. Directly above the Earth, perpendicular to the ecliptic, you'd first pass through the thin disk of asteroids and planetary orbits. Then you'd enter the thicker zone of Kuiper Belt and scatter disk objects with their elevated inclinations. Then you'd pass through a relatively empty transitional region. Then you'd enter the inner Oort Cloud, which might be slightly flattened. Then the outer Oort Cloud, which is fully spherical. Then, finally, you'd leave the solar system entirely and enter interstellar space. The journey from Earth to the top of the solar system, straight up from the ecliptic, would cover more than 1.6 light years. That's roughly 15 trillion kilometers. And most of that distance would be crossed in near total emptiness, with the occasional icy body drifting invisibly in the darkness. It's worth pausing to appreciate just how different this picture is from the flat diagram you grew up with. The flat diagram shows a disk maybe 15 billion kilometers across, centered on the sun, with the planets arranged neatly along it. The real solar system is a sphere roughly 30 trillion kilometers in diameter, with the planets occupying a tiny flat region at its center, and the rest of the volume filled by the spherical Oort Cloud. The flat diagram shows less than 1% of the solar system's true spatial extent. It's like drawing a map of the United States that shows only a single city block and calling it complete. What lies above and below the solar system, in the most literal sense, is the same thing that lies around it. The Oort Cloud. A vast spherical, sparse, cold, dark collection of trillions of icy objects, stretching in every direction for more than a light year. These objects are as much a part of the solar system as Earth or Jupiter. They orbit the sun. They're made of the same primordial material. They've been there since the solar system formed, exiled to the outer darkness by gravitational interactions with the giant planets during the chaotic early history of the solar system. They're the most distant members of our sun's family, and they surround us completely, above, below, and on every side. The Oort Cloud is not just the answer to what lies above and below the solar system. It is the answer to what the solar system actually is when you step back far enough to see its full extent. The planets are the core. The Kuiper Belt is the thick ring around the core. And the Oort Cloud is the vast sphere that encloses everything else, defining the true size and shape of our home in space. It transforms the solar system from a flat disk into a three-dimensional sphere embedded in the galaxy. And that galaxy, as we're about to discover, adds yet another layer of meaning to the question of what lies above and below us. Because the solar system doesn't exist in isolation. It sits inside the Milky Way, tilted at an angle to the galactic plane. And when you start asking what's above and below the solar system in the context of the galaxy, the answer opens up into something even more vast and even more humbling than anything we've explored so far. Now we zoom out one final time We leave the solar system entirely, Oort Cloud and all, and we look at where our entire cosmic home sits within something far larger, the Milky Way galaxy. Because up until now, every time we've talked about above and below, we've been using the ecliptic plane as our reference, that invisible flat surface defined by Earth's orbit around the Sun. And within the solar system, that reference works well enough. It tells you where the planets are, where the Kuiper Belt thickens, where the Oort Cloud surrounds you. But the ecliptic plane is not the only plane in the cosmos. It's not even the most important one. The Milky Way galaxy has its own plane, the galactic plane, defined by the flat disk of stars that makes up most of the galaxy's visible structure. And here's what most people never consider. The ecliptic plane and the galactic plane are not the same. They're tilted relative to each other by about 60 degrees. Let that sink in for a moment. The flat disk of our solar system is tilted at roughly 60 degrees to the flat disk of our galaxy. If you imagine the galactic plane as a vast horizontal table, the solar system's ecliptic isn't lying flat on that table. It's propped up at a steep angle, like a dinner plate leaning against a wall. What counts as above in the solar system doesn't match what counts as above in the galaxy. The north pole of the ecliptic, the direction you'd go if you traveled straight up from the planetary orbits, points in a completely different direction from the north pole of the galaxy. These two norths are separated by about 60 degrees on the sky. This means that the question of what lies above the solar system has two very different answers depending on which reference plane you're using. If you mean above the ecliptic, you're heading roughly toward the constellation Draco. If you mean above the galactic plane, you're heading roughly toward the constellation Coma Berenices. These are different directions in space, pointing toward different regions of the cosmos, encountering different stellar neighborhoods, different structures, different densities of stars and gas. The simple word above becomes ambiguous when you realize that there are multiple legitimate reference planes to choose from. Let's explore the galactic plane first, because this is the larger and in many ways more fundamental reference. The Milky Way is a barred spiral galaxy, roughly 100,000 light years across and about 1,000 to 2,000 light years thick in its disk. It contains somewhere between 100 billion and 400 billion stars, along with vast amounts of gas, dust, and dark matter. The visible structure of the galaxy, the part you can see as that band of light stretching across the night sky, is concentrated in a relatively thin disk. This disk is the galactic plane, and it's defined by the overall rotation of the galaxy's stars, gas, and dust around the galactic center. The Sun sits within this disk, about 26,000 light years from the galactic center, in a region called the Orion Spur, a minor structure between two of the galaxy's major spiral arms. We're not at the center of the galaxy. We're not at the edge. We're roughly halfway out in a relatively quiet neighborhood where stars aren't too densely packed, and major disturbances like supernova are relatively infrequent. This unremarkable position might actually be ideal for a planet harboring life, since the inner galaxy is more radiation intense and the outer galaxy is deficient in the heavy elements needed to build rocky planets. The Sun sits very close to the galactic midplane, the exact center of the galactic disk. current measurements place the Sun about 50 to 80 light years above the galactic midplane, which sounds like a lot until you remember that the disk itself is 1,000 to 2,000 light years thick. We're barely off-center. In cosmic terms, we're right in the middle of the galactic disk. But the Sun doesn't stay at the same height above the galactic plane. It oscillates. As the Sun orbits the galactic center, the combined gravity of all the stars, gas, and dark matter in the galactic disk pulls it toward the midplane. If the Sun is above the midplane, gravity pulls it back down. As it passes through the midplane and continues below, gravity pulls it back up. The Sun bobs up and down through the galactic disk like a horse on a carousel, completing one full vertical oscillation roughly every 60 to 70 million years. The amplitude of this bobbing is estimated at about 200 to 300 light years above and below the midplane. This vertical oscillation carries the entire solar system with it, Oort Cloud and all. So the solar system isn't just orbiting the galactic center horizontally, it's also bouncing up and down through the galactic plane over tens of millions of years. At some point in its history, the solar system has been well above the galactic plane. At other times, well below it. Right now, we're near the midplane, slightly above it, and heading upward. Some researchers have speculated that this oscillation might have biological consequences. When the solar system is near the galactic midplane, it's in the densest part of the galactic disk, surrounded by more stars, more gas, more dust. This means more potential gravitational perturbations to the Oort Cloud from passing stars and molecular clouds, which could send more comets into the inner solar system, increasing the impact rate on Earth. When the solar system is farther from the midplane, above or below the disk, these perturbations decrease. Some studies have claimed to find correlations between the Sun's vertical oscillation period and the timing of mass extinction events on Earth, suggesting that passage through the dense mid-plane triggers comet showers that cause mass extinctions. This idea is controversial and not universally accepted, but it illustrates how the solar system's vertical position within the galaxy might have real consequences for life on Earth. Now, let's ask the big question in the context of the galaxy. What lies above and below the galactic plane? If you traveled straight up from the galactic disk, perpendicular to its surface, what would you encounter? The first thing you'd notice is that the density of stars decreases. The galactic disk concentrates most of the Milky Way's visible stars in a thin layer. As you move away from the mid-plane, stars become less common. The thick disk, a somewhat older and more diffuse population of stars, extends farther from the mid-plane than the thin disk, reaching up to about 3,000 light years above and below. But even the thick disk eventually thins out. Beyond the thick disk, you enter the stellar halo. The galactic halo is a roughly spherical region surrounding the disk, extending tens of thousands of light years above and below the galactic plane. The halo contains old stars, many of them among the oldest in the galaxy, formed more than 10 billion years ago when the Milky Way was young. These halo stars are metal poor, meaning they contain fewer heavy elements than stars in the disk, because they formed before earlier generations of stars had enriched the galaxy's gas with heavy elements. The halo also contains globular clusters, dense spherical collections of hundreds of thousands of stars. About 150 globular clusters are known to orbit the Milky Way, scattered throughout the halo. Some are relatively close to the galactic plane. Others orbit at enormous distances, tens of thousands of light years above or below the disk. These clusters are ancient, typically 10 to 13 billion years old, and they trace the structure of the halo like ornaments on a Christmas tree, revealing its shape and extent. But the halo isn't just stars and globular clusters. It's mostly dark matter. The Milky Way's dark matter halo is thought to extend far beyond the visible stellar halo, reaching out to perhaps 600,000 light-years or more from the galactic center. This dark matter halo is roughly spherical and contains most of the galaxy's total mass. We can't see dark matter directly, but we can detect its gravitational effects. The way stars orbit in the outer parts of the galaxy, moving faster than they should based on the visible matter alone, tells us that there's a vast invisible mass surrounding the galaxy, holding it together. So if you traveled straight up from the galactic plane, you'd pass through the thin disk, then the thick disk, then the stellar halo with its old stars and globular clusters, then the outer reaches of the dark matter halo. The stellar density would drop rapidly once you left the disk, and by the time you were a few thousand light years above the plane, stars would be sparse, tens of thousands of light years above the plane. You'd be in the deep halo with only occasional old stars and globular clusters scattered through a vast space dominated by invisible dark matter. And beyond the dark matter halo, intergalactic space, the void between galaxies. This is the emptiest environment in the known universe. The density of matter in intergalactic space is extraordinarily low, roughly 1 atom per 10 cubic meters. It's not perfectly empty. There's a thin intergalactic medium, mostly ionized hydrogen, stretched across the vast distances between galaxies. But it's so sparse that for all practical purposes, it's a vacuum. In intergalactic space, looking back down at the Milky Way, you'd see our galaxy as a luminous disk with spiral arms, a bright central bulge, and a faint extended halo. The solar system would be completely invisible, an imperceptible dot on one of the minor spiral features. Earth would be beyond any hope of detection. Looking outward, you'd see other galaxies. The nearest large galaxy, Andromeda, would be visible about 2.5 million light years away. The Magellanic Clouds, satellite galaxies of the Milky Way, would be visible as fuzzy patches. Dozens of smaller dwarf galaxies would be scattered around, some close, some distant. This is what lies above the solar system when you follow the direction to its ultimate conclusion. Start at Earth, travel perpendicular to the Ecliptic, pass through the Oort Cloud, enter interstellar space, continue upward, now perpendicular to the galactic plane, since the ecliptic is tilted relative to it. Pass through the galactic disk, rise into the stellar halo, continue into the dark matter halo, leave the galaxy entirely, enter intergalactic space, and eventually encounter other galaxies, other clusters, other superclusters. There's no ceiling, no boundary, no wall. Just an endless expanse of space containing structures at every scale, from individual stars to galaxy clusters to cosmic filaments stretching billions of light years. But here's the crucial insight that ties everything together. There is no real above. There is no real below. These concepts are inventions of our terrestrial experience, products of living on the surface of a planet where gravity defines a clear and consistent down. In space, away from any single gravitational source, there is no preferred direction. There is no up, no down, no above, no below. There is only space, extending equally in all directions. When we talk about what's above the solar system, we're implicitly choosing a reference plane, usually the ecliptic, and defining above as one of the two directions perpendicular to it. But this is a choice, not a physical reality. We could just as easily use the galactic plane, which would give us a different above, or the invariable plane of the solar system, which would give us yet another slightly different above. Or we could orient ourselves relative to the cosmic microwave background, the faint radiation left over from the Big Bang, which fills the universe almost perfectly uniformly in all directions and has no preferred plane at all. The concept of direction is relative in a deep physical sense. Einstein's general theory of relativity tells us that space and time are curved by mass and energy. There's no absolute coordinate system painted on the fabric of space. Directions only have meaning relative to something, relative to the local gravitational field, relative to a rotating body, relative to a chosen reference frame. In the solar system, we choose the ecliptic. In the galaxy, we choose the galactic plane. In the universe at large, there is no natural choice at all. This isn't just a philosophical point. It has real practical consequences. When astronomers map the universe, they have to choose a coordinate system, and different systems reveal different aspects of reality. Ecliptic coordinates show the solar system's structure, but obscure the galaxy. Galactic coordinates reveal the Milky Way, but hide the ecliptic. Each coordinate system is a lens. None is more fundamental than any other. The fact that the ecliptic is tilted 60 degrees relative to the galactic plane means that the solar system's above and the galaxy's above point in very different directions. If you define up as perpendicular to the ecliptic and travel in that direction, you'll be heading at a steep angle through the galactic disk, not straight out of it. You'd eventually leave the disk, but not by the most direct route. Conversely, if you define up as perpendicular to the galactic plane and travel that way, you'd be heading at a steep angle relative to the solar system's ecliptic, not perpendicular to it. The two reference frames don't align, and this misalignment is a vivid illustration of the fact that above is not an absolute concept. There's another layer to this. The Milky Way itself is moving through space. Our galaxy is part of the local group, a collection of about 50 galaxies, and the local group is part of the Virgo supercluster, which is part of an even larger structure called Laniakea. All of these structures are moving relative to each other and relative to the cosmic microwave background. The Milky Way is falling toward the center of Laniakea at about 6